Alright, in this example we're looking at a mobile, basically an artistic structure that's hung from the ceiling, roof, or something of that nature. And in this case we have like a rope hanging at a certain point with a large 10 kilogram mass that's hanging on the left side, a 2 kilogram mass that's hanging on the right side, and a mystery mass that has to be suspended from that location. And what we're wanting to know is how much mass is needed to be hung at that location in order to achieve static equilibrium. The plank itself will have mass, and that means it will have that mass's weight acting at the center of gravity. So in order to find out more about what's going on, let's get some measurements. Every 2 squares is about half a kilogram, so it means every 4 is a whole kilogram, and also every 4 is a meter. So I've set this ruler up so that every 4 is a whole. So we find out that it's about 2 meters to the rope. It's another meter over to where we're having a mystery mass hanging, and then the whole thing itself is 5 meters long. And of course the halfway mark could be 2.5 meters. So the next step would be to go ahead and make our drawing, after of course we wrote that down. Our drawing itself will be a very simplistic drawing. It's just the plank itself. We don't concern ourselves with the weights. We don't concern ourselves with the rope. We just want to draw that which was going on to the plank, the thing that could be rotated, or the thing we don't want to rotate. So in that case, I have the weight of the 10 kilogram mass on the left. I have the weight arrow of the 2 kilogram mass on the right. And I also have the 2 weights in the middle, which is the weight of the plank acting at the center, and then the weight of the mystery mass. Now I'm not sure exactly how big this should be, but understanding that there is a 10 kilogram object on that side, then there probably would be requiring quite a bit of weight right here at the mystery mass location. Not only that, but I also drew the distances. Now the distances, well, they're kind of focused around this string here, this tension. The reason why that's important is because, well, I'm not going to want to use that in my torque equation. So it's kind of a little foreshadowing there. Now I'd want to make sure I have a label drawing. And again, I actually know these numbers. I don't have to put x1 and x2 and all this that's symbolic. I could actually put numbers, like I know that the total length is 5, and I know that that's 2, so I could say this is 3, that's 2, and this, because it's half of 5, would be 2.5 minus 2, which is just 0.5. I could also put in here that this would be at a 1 meter distance location. Now I didn't do that, but it would probably be faster to do that. Just put in the numbers and then plug those numbers into the equation. I did it this way so we could actually focus on like the algebra behind it. But again, if we're talking about doing it fast, put in those numbers that you have from the drawing. That will actually make it a little bit faster than what I'm doing and what I'm showing here. Now the next step after the drawing is to focus in on the physics concept. And again, this is a plank that we like to keep in static equilibrium, which means we have to meet the conditions, which is net force is equal to 0. That's x and y forces have to add up to be 0. And in this case, there are no x forces, so all the up forces, all 1 of them, and all the down forces, all 4 of them, have to add up to cancel each other out. Now the next condition is that the torques have to be adding up to give you 0, which means there can be no torque or a force acting at a distance from a pivot point that would cause rotation to change. So with the equations, we do the forces, which again, like I said, all the weights acting down against that one tension. And the torque, first we got to pick a pivot point. And in this case, like I'd stated before, the pivot point is going to be on that tension rope, because we don't know what it is, nor would we want to actually have to include it in the equation for torque, since how it's another unknown. Although we do know it's the weights of all the other masses, according to the sum of forces equation, but we don't know what one of the masses is. So I would place my pivot point right there in order to take that out of the torque equation and help us avoid another unknown. So when you do that, and you do the force times the distance of application, you wind up finding various torques. So here's the torque of the 10 kilogram object times the distance away from the pivot point we picked, which is x1. And then of course here's the torque that's provided by the plank itself times how far it is away from that pivot point. And then here's the weight of the mystery mass times how far it is away, x2. And then of course the last one being the torque of the 2 kilogram mass, and that's at a distance of L minus x1. Now again, in this case, plugging in the number for the distance, since how we know it, would be a lot faster. But what I'm trying to do is show you the algebraic setup first. Now, in contrast to what I just said, typically you'd want to hold off on the numbers, except in a case where it'd make it faster. So maybe not, so don't put in the numbers? Maybe, I don't know. I think it's definitely going to be faster if the numbers go in at that particular point. So let's take a look at the next step, which is the algebra. Now again, the not knowing the tension and not knowing the mass, it makes working with the sum of forces equation kind of problematic. Too many unknowns. So what we're doing instead is looking at the torque because it only has one of the unknowns, that being the mass that we're looking for. So next step would be to actually isolate that mass all by itself, or at least that term. So you can do that fairly easily by moving all the terms except for that term on the other side of the zero. Or you could just move that term on the other side of the zero. You have options. In this case, I actually chose to keep it where it is and move everything else. And by doing that, I'm going to add one more step to this whole process. Now, once I have the terms moved over, you'll notice that there is a g in every single term. I can get rid of that g, which brings the equation down to just being distances times the masses. The next step would be get rid of that negative. So that would be avoided if I had just moved over the m2gx in the first place instead of moving everything else over. Now, the next step on this one is just to divide by x2. There's my final equation. Now all I have to do at this point is plug it in with numbers. So once I plug all the numbers in, you quickly see that it's fairly easy math. No need to use a calculator in this case. Because what it boils down to is we need an 11.5 kilogram mass located at that location 1 meter away from the string in order to keep this in static equilibrium. Now if we want to know what the tension was in the string, we now can use that mass in the sum of forces equation in order to figure out what the tension should be. But that's it. That's how you do that problem.